Hello guys, welcome again to this basic power system. So in last lecture we have completed single line diagram. So in this lecture we will be covering transmission line performance. So uh, let's go to the topic. So transmission line performance. Okay, before I start this lecture, I would like to request you subscribe this channel if you have come here for the first time. Okay. Uh, I'm uploading some basic power system lecture videos now. We'll be coming with some advanced power system and advanced power system lecture also, of course. So, if you are interested in power system, basic electrical engineering, and uh, s- topics related to electrical engineering, you can subscribe this channel. I'll be uploading videos on basic electrical as well as basic power system, advanced power system. Okay, so let's start. So transmission line performance. So as you can see, it's a simple transmission line where AC source is connected and load is connected, and between these two, there are transmission lines. It's connected through the transmission line. Okay, the source and load. So the performance of transmission line is measured by two parameters. Okay, the performance of the transmission line is measured by two parameters. First one is efficiency, and second one is voltage regulation. So these two are the efficiency and voltage regulation we need to calculate for transmission line performance actually. Okay, so percentage of efficiency percentage of efficiency calculation formula is simple here. As you can see, is power delivered at receiving end by power delivered at sending end. Okay, simple thing. This is this is the sending end. Okay, this is the sending end, and this is the receiving end. Okay, this is the receiving end. This is the sending end because power is we are sending from this AC source and it's coming to this load. Okay, so as that simple it is. So percentage of efficiency is power delivered at receiving end. Power delivered at receiving end by power delivered at the sending end. Okay, is equal to, we can say that power delivered at receiving end is by power delivered and receiving end plus loss. Okay, so when we are sending sending power or or transmitting that power from this source to load. Okay, so there are some losses. Okay, there are some losses, so that loss is the loss. Okay, is loss plus the power we are receiving at the end, sending end. So that is the total power. Okay, that is the total power we are sending from the sending end. So same thing here. I think it's clear. So percentage of efficiency we can write in equation P by P plus 3 I square R. Okay, P by P plus 3 I square R. I square R is the loss formula. Okay, I square R. We have added 3 I square R because this is, we are considering a three wire transmission line. Okay, this is a three-wire transmission line. Okay, this is just representation, okay, of single line diagram of this three-phase transmission line, uh, transmission line, or three-phase power system. Okay, so got it. Why we are using 3 I square R, but loss for all three phases. Okay, 3 I because of three-phase line. So now regulation, voltage regulation. What it is? It is the change in voltage from full load to no load. From full load to no load. Okay, when the load is full. Okay, full load, all the loads are connected. That is, we are saying full load. Okay, or you can say the maximum load demand when it is connected. from that condition to when there is no load. When in the transmission line, suppose there is no load. So in between the change in voltage, that is called the voltage regulations. Okay, is it clear? So here we can see the same diagram we have drawn here. That's AC source. This is the sending end. Okay, this is the receiving end, and we have added one here switch. Okay, S1. In this figure, you can say S1 switch is added. So we have opened this switch. Okay, now there is no load. At first, this is full load condition. Okay, full load, and this is no load conditions. Okay, so now in between there is some voltage changes from full load to no load. Okay, so that voltage is called voltage regulations. Okay, so here if we measure the voltage here VR, okay, and here V. So I was watching cricket. So voltage regulation will be full load to no load, VR minus V1 R. Okay, this is the voltage regulations. Okay, is it clear? The same diagram, the same figure, circuit diagram. Okay, we have added one switch to, and we have turned on this switch to just make it open circuit, so there is no load connected. Okay, circuit is not connected circuit. Okay, yeah, here you can see the regulation, percentage of regulation. The equation, the full equation is given here. The percentage of regulation, percentage of voltage regulation, you can say, is equal to VR minus, sorry, it will be V small r. Okay, it will be V small r. So it will be VR minus VR by VR into 100 for percentage. Okay, clear? This is the equation for voltage regulations. Okay. So voltage regulation is the change in voltage from full load to no load. Full load, here circuit is connected totally. Okay, it's full load conditions we are assuming, and here we are adding one circuit. Okay, this is one circuit, and this circuit is open. So now it's no load is connected to this source, that is a no load condition. Okay, we are just trying to keep everything is simple. Okay, just trying to clear the basic things. Okay, you get some you can get some idea if you are going to start this, or if you are revising also, you are just getting some basic things. Okay, so now we know, we'll calculate little bit, will be say we'll see little bit calculations. Okay, velocity of traveling wave, we know V is equal to F lambda. Okay, this is from physics. Okay, velocity of traveling wave V is equal to F lambda, or we can say velocity, that is 3 into 10 to the power 8 meter per second, is equal to 50 lambda. Okay, 50 we have used because 8 we in India we normally use 50 hertz frequency, this frequency. Okay, and from here we can calculate lambda. Lambda, it will come 6,000 kilometer. Okay, 6,000 kilometer. Okay, it will come at first at meter, then we have calculated in kilometer. Okay, 6,000 kilometer. So voltage current values are not same at different point of transmission line. So you can see this graph. Okay, this graph, look at this graph. the there is one full wave 6,000 kilometer. Okay, this is distance 6,000 kilometer. That is one AC wave, sinusoidal wave. Okay, so if we follow this wave, okay, we can easily see the value or voltage or current are not same at different point. Okay, is it clear? Not clear? Suppose here it's different value at this point. At this point, some different. At this point, zero. Then it's increasing. At this point, it's a maximum. Okay, at this point, it's coming down again. Different value. Here again zero. Okay, here maximum. Here again coming. It's zero. So at different point, the voltage, if we consider it is a voltage signal or the current signal, the value is not same. Value is not same. Okay, is it clear? From this graph, we can say at every point it has different value. Now, if length is less, if the length we assume it's less, okay, so just assuming up to 200 kilometer. So variation is very less. We can say from here to here, we just are considering here to here, only this distance compared to this full wave, there is so many changes in value. So if we are considering only small portion, only 200 kilometers, so variation we can say it's very small. Okay, clear, no? Simple thing. The same graph you can see here. We are just considering only small portion, only small distance, that is 200 kilometer. So we'll get very less variations in the value of voltage and current. Okay, so now let's see different types of components of transmission line. We are not going to all the components, only these. Okay, series component and shunt component. These two, based on the connections, how the components are connected in the transmission line. Okay, series component, resistance is connected in series and inductance is connected in series. Okay, L R C. Okay, series component are resistance and inductance, but shunt component are capacitance and conductance. And conductance, as you can see here, value of conductance is very less in practical and it is negligible. So, okay, in practical, the conductance value is very less, so we can neglect the value of conductance. Okay, for capacitor, due to capacitance, charging current pass through it. Okay, for capacitor, look, the capacitor are connected in parallel. Okay, this is the transmission line. Okay, this one is the earthing. So capacitor are connected in parallel, and due to this capacitance, charging current, that is IC, pass through it. Charging current of this capacitor is passed through it. IC is the charging current. It must be written like this, IC. Okay, so IC is equal to V by XC is equal to V by J omega C, and from here we can add V omega C. We can write it down. Okay, I'm just watching cricket. So here we can write it down. omega is equal to 2 pi f and omega both constant. Okay, this is omega. It will become omega is equal to, sorry for the mistake. Omega is equal to 2 pi f. Okay, omega is equal to 2 pi f. F and omega both constant because f is constant. Okay, if constant, why? It's we use 50 frequency in India, so it's constant value. So omega will also become constant. Okay, is it clear? So from this equation, IC is equal to V omega C. We can write IC. We can see IC is very directly proportional with voltage. Okay, directly IC, this charging current of capacitor is directly proportional with voltage. Okay, if voltage increase, that will also increase. If voltage decrease, that will decrease. Okay, IC will decrease. And this C also, omega we got constant, so C also, the capacitance value IC is also directly proportional with capacitor. A capacitor formed at every point as the length. So capacitor is directly proportional with L also. Okay, this is the length of the transmission line. That's why we are saying capacitor are formed at every point as the length increases. Okay, as the length increases, capacity number of capacitor also increases in the transmission line. So capacitance value, total capacitance value, it will also increase. Okay, with the line. So it's directly proportional with the length of line, transmission line. So we can say if IC is directly proportional with C, that means IC is directly proportional with the length of the transmission line also. So V and L is high. If V and L is high, we can't ignore C. Okay, in analysis or in calculation of performance, transmission line performance, we can't ignore C when the value of voltage and the transmission line length is high. You got it? Okay. So there are mainly three different types of transmission line based on length. You can say mainly based on length. Okay. Short transmission first. Let's see. Short transmission line. We will not go for full analysis. Okay. Full calculation will not go. Maybe we will come with in advanced power system with the full calculation. Otherwise, the video will be so lengthy. Okay. If we add those three calculations for three different transmission line. So first of all, for short transmission line, when we say it is a short transmission line, when the length is greater than 20, okay, kilometer, greater than 20 kilometer, but it's less than 80 kilometer. Catch, nice catch. Length is greater than 20 kilometer and less than 80 kilometer or transmission line length, and voltage is less than 20 kilovolt. Okay, then we can say it's a short transmission line. And here C can be neglected because voltage is also low and length is also low. So in analysis we can neglect voltage, capacitance. Okay, capacitance value. We'll consider only resistance and inductance, and we can go for lumped analysis. Okay, for the analysis of this short transmission line. It's okay. Here is the graph of one short transmission line where only resistance and inductance value will calculate. Okay, only resistance and inductance value will consider for the calculations. This is the sending and current, this is receiving end current, this is sending in voltage, and here receiving in voltage. Okay, this is the diagram of one short transmission line for the analysis. Okay, simple diagram for analysis. Now next is medium transmission line. Okay, so when we'll call it a medium transmission line, when the length of the transmission line is between 80 to 200 kilometer. Okay, that means greater than 80 kilometer. The length is greater than 80 kilometer, but less than 200 kilometer. Okay, and voltage is greater than 20 kilovolt, but less than 100 kilovolt. Okay, so this is the parameter for medium transmission line. Again, one more wicket. I think. Okay. See, see, so C is divided. C is divided at both end. We can do two types of calculation actually. Look here. So first we can go for like this. C is divided at both end, and another one we can say C is at the middle of resistance and inductance. Okay, or maybe we can divide this resistance and inductance. Okay, so this diagram, if we go for this analysis, we can say this is nominal pi method. Okay, and this is nominal t method. Okay, where C now in nominal pi method C is divided at both ends, and R and XL is divided into half. Okay, R and XL is divided into half. Here it's clear from the diagram. Okay, now long transmission line. So what are the parameters for long transmission line? Is length is more than 200 kilometer. Okay, length is more than 200 kilometer and voltage is more than 100 volt. Length is more than 200 kilometer and voltage is more than 100 volt kilovolt. Okay, 100 kilovolt. So we can say it's a long transmission line. So for analysis, we have to go for distributed parameter. Okay, we can't neglect that capacitance. Okay, because here the voltage and transmission line length both are high. Okay, so we have to go for distributed parameter. Here you can say C. At every point of transmission line length, there is capacitor is connected. Okay, and in between that, resistance and inductance are there. Okay, if we write it down R1, XL1, then it will be R2, XL2, then it will be beta R3, XL3. You can write it like that. For C, it will come at 1 by C1, 1 by C2, 1 by C3, 1 by C4, like that. 4. Okay, we are not going in details in analysis. Maybe we will come with different uh, video. Okay, lecture for a specific short, medium, and long transmission line analysis. Okay. So that's it for today. If you have any doubts, you can comment in the comment box. Okay, I'll try to reply you first. And if you have come here for the first time, I would like to request you to subscribe this channel. Okay, we are only this is only basic advanced power system. Okay, not advanced power system, it's basic power system. We are just covering the basic things. Okay, only if you are like experience, you have gone through all of this, maybe you feel like it's nothing, but whoever not has gone through not gone anywhere, or who is coming for the first time for this power system class. Okay, It will be helpful for them to yeah, after watching this video, you will start uh, going for books. Okay, it will be easy for them. They'll get some idea from here. And my humble request to everyone is please plant just only one tree each day, or sorry, only one tree at in a week, or if you are not able to like get free days, so Sunday is there, this holiday, you can consider the Sunday. Just plant only one tree, because I think the only way to fight against global warming is to plant trees. Okay, that's it, guys. So PPT is available for if you want to keep it as note, you can request me. Okay, so you can connect through me this mail. And in next lecture, we'll be covering this transmission and distribution systems. We'll go through the basics. Okay, and after that, we'll cover this high voltage distribution line. And after that, we'll come with some advanced power system process. Okay, so bye bye, guys. Enjoy.